Hello everybody! I hope everyone's having a wonderful day. I think today we're hanging out with the crickets again. But anyways, last day we were talking about how we can build a heap bottom up. So if I give you an array, you'll be able to turn it into a heap. So I talked about Heapify last day and we did an example. So I showed you how it builds it bottom up. So you start off with each one of the nodes and you imagine it's subtree. And what we do is we use this bubble down procedure to fix anything that happens beyond each one of its parents. Now, I told you that this thing takes linear time. Now, on a very naive inspection, you look at this and say, okay, well, how many times does this loop iterate? And you say, okay, well, it's roughly about half, right? So it says n minus 1 over 2, which n is the number of nodes or elements. So what I do is I perform bubble down. Bubble down we know takes a log n time in the worst case. If we're particular here. And then I do this at least n over 2 times. A naive analysis would yield out n log n. I'm going to show you how you can actually get it down to n. So what we're going to do is, so we're going to consider its analysis here. Now, the big observation I want you to make is when we did that procedure last day, did we do bubble down from the root every single time? Did we do it every single time from the root? No, we did not actually. What we did was we started at the parent of the last node that was put in. It could be any one of these ones here. I start at the parent there, and then I do bubble down from that one, right? I don't do it from up here. I only do it on partial heaps. So these heaps that I'm building bottom up, I only do it on the subtree's root of each one. So I do it here, I potentially do it here, and I do it here. But I don't do it really down here much, right? But the point is that I can actually bound this in a little bit of a smarter way by noticing that. So I'm going to say, notice that we apply bubble down only on smaller and growing. Because you would agree with me that what we do actually is we build these heaps, and what we do is we merge them every single time we introduce another one of these parents, right? And growing heaps. So there's two observations I want you to observe. So the first one you should obviously see is that, remember, when we do bubble down, how many times, what's the time complexity if you think about it in terms of the number of ancestors? We know it's big O log n when you look at the entire heap, but how long does bubble down actually take? So remember, bubble down is where we can consider each one of those children and we pick the bigger of them. We do that each time. So how long does it take if I know the number of ancestors is only so many? So imagine I gave you some height. It should take big O of I, where I is the height of the heap, right? So we had log n as the total height of the heap, but just for a given height I, it is big O of I, right? Now, the second observation I want you to observe is really how many times how we deal with bubble down, right? So I want you to think about the maximum number of elements in a heap of a given size. So what I want you to think about is, let me just write something down here and then we'll look at this picture here I'm going to have. So the maximum number of elements in a heap of size n is equal to 2 to the power of I plus 1 minus 1. You'd agree with me that we established this idea actually last class, not last, yeah, well, it was the class before that. We showed that the height was log n. We used this property when we were trying to find an upper bound on the number of nodes in the heap. Remember? It's when it looks like this, right? So how many nodes are there in a heap of size n whose height if rooting its subtree is I. So what do I mean by this? Well, all the nodes, now if you look at the subtrees rooted by each of these leaves, what's the height of, say, this subtree? It's 0, right? It's 0. So all of these have height 0. If you think about them in terms of subtrees rooted at each one. How about these ones? All of these, if I were to take the subtree of this node, it would be all of these ones down here, which means that the height is 1, right? And naturally, this would be height when it's 2. So we know that in this heap here of height 2, we know how many nodes there can possibly be in it, right? It's 2 to the I plus 1 minus 1, where I, it would be in this case the total height of the tree. So what would that be? Actually, let's start down here first. We know that when you have the array, and you imagine it can be cleanly divided, how many nodes can possibly be in the bottom level? Well, it's the total number of nodes, right? In this case, it's 2 to the power of 3 minus 1, all over 2 to the power of 1. So it's about half of them, right? So remember, this is the total number of nodes in the heap. This is how many we will have when we consider the leaves, right? Naturally, each one of these has a parent. How many parents are possible when you have this many leaves? Half that number, right? Because if I have these being multiples of 2, that means I have to divide it by 2, and now tell me how many parents there are. This is 2 to the power of 3 minus 1 raised all with 2 squared. Because I just divided by 2, right? And how about the roots? How many would be here? Well, this would be 2 to the power of 3 minus 1 all over 2 to the power of 3, which is equal to 1 when I round it up. Remember, this is the ceiling. I'm just using a ceiling here. So I have a way of talking about the number of nodes at a given level. So if I look at how many nodes are at a given level with a given height, for which how many nodes it has beyond there. So if I look at the subtree with height 1, how many nodes are possible at that level in this total heap of size n? Well, this is the relationship right here. So if I take this and put this all together, because keep in mind, I have all my levels here. What I need to do is just sum over this. Remember, n is equal to this. So I'm just going to have a nice formula for this, right? So by summing over all levels, all the levels of the tree, the total time Heapify takes when the tree has height h is the following. So what we're going to do, I'm going to take these two observations. Actually, I'll leave this here. We don't really need Heapify at this stage. I'm going to leave those at there. So remember, we have these two observations. The burning time will bubble down for a given height. And then I have it where the max number of elements in a heap of size n is equal to this. I asked how many nodes there are of a heap of size n at whose height is I. So I want to know how many nodes there are at that given level. You got to look at it like the levels. I'm trying to count those up. Because remember, each one of those will have some relationship with bubble down. Because I'm just trying to bound how many nodes there are at a given level. So, when I take them all together like this, I'm going to sum over all of them. So I'm going to imagine I go from where I have all the nodes at height 0, height 1, height 2, and so on. Keep in mind I'm being overly generous with the way I'm doing this. I'm going to be somewhat informal, so I'm going to use that somewhat more informal way of writing out the big O's, which will be okay for our context, because I've told you how to use it. Now remember, I told you that n is equal to 2 to the I plus 1 minus 1. So all I would have to do is just put in my relationship here, right? Remember, those are what I derived over on this side. So that was the number of nodes in a heap of size n whose height, which would be the subtree. If I take its subtree, what its height is, how many could there be at that given height? Another way you can think about it is how many are at that level where the height would be the respective subtree's height of the node in that level. It's very, if you have any questions about this, don't be afraid to ask me. There's a lot of terminology and jargon in this analysis. The point is that you look at the nodes at each level, and I'm asking in relation to n how many nodes there are at a given level in the heap. That's really what I'm trying to get at. So, for each one of these, I would consider how many nodes for a given height. Well, I know that the height is big O of I for height, that given height. And then what I do is I just simply know how many nodes are happening at that height. Remember, we build it level by level up, right? And I know each one of those takes big O of I. So I'm multiplying those two things together. And then I have, so this is, now remember this is in this context, n times, so what I'm going to do is, see, all of them are multiplying and I have n here, but it's happening in all of them. So what I'm going to do is I'm going to just throw that out front of the summation, because every single one is multiplying at some point by n, which n is irrelevant to what I is doing. Except on top of that, there's a ceiling here. Now technically, because of the ceiling, you would have to be a little bit more particular, but in big O, you can effectively get rid of these ceilings, assuming that they don't cause any strange behavior. They don't cause any strange behavior here. I'm going to skip some steps in that process, so I will not ask you to recite this analysis at all. I'm just showing you it. So I'm going to go from 0 to h. Remember, h is the height of the heap. Now, what do I end up with left? Well, by using big O here, I can not have to write any constants here. So I can just write I literally. And now I can kind of group the I and the 2 to the I plus 1 together. Now, it's worth noting this is 2 to the I plus 1. Now, I'll let you think about it, but if I just simply pull out an extra half, because this would be 2 times 2 times 2 times 2, I plus 1 times. So if I just factored out one of those 2's, which would make it a half, because it's in the denominator of this fraction, that's just another constant, which in big O terms, we get rid of. It's just a constant. So I don't claim this to be a simple analysis to understand. But if you're familiar with your big O properties, you'll see that you can actually make this step by a big O. Now, this is where it gets a little funky. What I'm going to do is I'm just going to ignore H, because this summation actually has a very special property to it. I'm going to explain in a moment. Instead, I'm going to make an infinite sum from I, all I over 2 to the I, just like I had before. But now you would agree with me that H is most definitely not infinite, right? It's some finite number. So if I take this summation, this should most definitely be at least, like this should be bigger than that at least, right? So I'm being very charitable. Now there's a very neat thing about this. Now you might say, well Dan, that's summing over an infinite number of terms. That seems really strange. Now this is where it gets very particular. This is why knowing things a bit more about continuous maths, or things like calculus and sequences and series, this stuff sometimes creeps into analysis every once in a while. So I want to show you an example of this, because sometimes I encounter CS students that really just do not understand that sometimes the kind of mathematics you run into in other classes outside of CS sometimes creep into analyses. So I want to show you an example of this, just to open your mind to it. Now, this thing, which looks really strange, and I would never ask you to recite this summation by any chance. What this is actually, this is an infinite sum that actually converges to a value. What do I mean by converges? It means that this actually has a finite result to it. So, not to get too into the details, this is actually equal. So if I replace this infinite sum with this, I get that. Now it's worth noting that this comes as a result of the following infinite sum of I times x to the I, which is equal to x over 1 over x squared. And note that this is true if the absolute value of x is less than 1. So this is what I'm using to get this. So this is an infinite sum that does indeed have a value. But it only is for certain values of x in here, and our x here is what? It's 1/2, right? So, because you can clearly see that, right? I have I here, and I just pull that off to the side, and I have 1/2 to the I, and there it is. So if you evaluate this, you'll realize very quickly, oh, okay, this is just some number. It's just some constant. But what is that? It's just big O of n, and we're done. Isn't that cool? So I would not ask you to recite this, but I really wanted to show you an example of how you can use this bit more informal big O like this. It's very useful. Do you see how it could be useful? So I can cut out some extra steps, but you have to be very careful when you do so. The other thing I wanted to show you is that just because it isn't something that looks like pretty thing you can analyze, there are ways you can bound it using a bit more mathematics. The dreaded M word. So don't be afraid of the M word. Don't be afraid of mayonnaise. Okay? So that concludes talking about Heapify. So now you know that Heapify, in fact, takes linear time, which is really nice. So you can do it all in one array. You never actually have to worry about having to build a separate heap. You can just turn the array into a heap. That brings me to talk about sorting. So I'm going to be fairly quick here. Now, the notes go into more detail, but I'm going to be somewhat quick with this. So, how can you apply something like this to sorting? So I'm going to say given an array n, A of n objects. And I'm going to assume that the objects obviously can be compared in constant time. And they obviously take some constant amount of space. Create a priority queue. So you're going to create a priority queue. So how can you do sorting? So I have some array A. And what I can do is I'm going to create a priority queue. What can I do to sort? Well, you're going to perform insert on each object where the value compared. Now, when I say value, I mean like of the object, not value as in the element. Value compared. Compared is the key. So what do you do after you do these insertions into the priority queue? You just use remove min, right? Just use remove min. You're just going to copy back into A from left to right. Received by a remove min call. So what you do is you just simply use remove min on the priority queue until it's empty. You copy them back left to right into the array and you'd be done. So if you just think about it that way, how long does this take? So it depends on the priority queue implementation. Right? It has to depend on that. So I want you to think about this. We talked about a variety of different ways of implementing a priority queue. We talked about a doubly linked list. You had an unsorted version and a sorted version. Now, here's the strange part about this. Now, you've learned probably about various sorting algorithms. I'm going to throw some interesting things that are going to blow your mind, hopefully, depending on how you implement the priority queue. So, if you use an unsorted list, how long should an unsorted list take? Well, each one of the insertions in an unsorted list takes constant time. However, every single one of the remove mins takes how much time? Linear time. So you have to perform at least n remove min, so it means it's going to take big O of n squared. Now, the neat thing about this is actually if you look at what the priority queue is doing, every single time you do one of these insertions and removals, believe it or not, this actually functions very much like selection sort. So it's not literally selection sort in the sense that it's like an array where you're doing the swaps. The point I'm saying is that if you look at the elements and how they get manipulated, it operates like selection sort, which is very strange to think about because normally you think of, oh, well, why would an algorithm that involves priority queues operate like a sorting algorithm? It's kind of strange to think about. But I want you to think about that a little bit. It's kind of interesting, isn't it? So you can almost look at this like a scheme for sorting. So this process of using a priority queue is intricately related to sorting, which is very strange when you think about it. But it is actually very surprising, and you'll see why. Well, if I have a sorted list, what happens in this case? Well, the brunt of the work happens in the insertions. Each one takes linear time. So it means that I have to do n insertions, so it means it's going to take quadratic time. I have to do n of them. And each one of those insertions takes linear time. Now, the interesting part is that this operates like insertion sort, if you think about it. So if you look at the elements and how they get put in, Every time I do an insertion, it's like creating a partially reconstructed list, and I put it into the appropriate spot. If you want to learn more about what I mean by this, because I'm not going to talk about this a whole lot in this course, you can take a look at the textbook and notes I give the pages for those if you're curious. No, I just recommend just playing around a little bit with the priority queue. Draw them out as doubly linked lists, or even just as arrays if you would like to do it that way. And you could just see how it operates, and you'd see that it's very interesting. So that brings me to talking about a heap. So if I use a heap, how long does it take for the heap? Okay, how long does it take for a heap? So I perform n insertions, now keep in mind, I could either do n insertions like this, or I can use Heapify. Either way, it's going to take something no longer than n log n, right? If you're going to do n insertions, each one takes log n time. Or I use Heapify, it takes linear time. Then I perform remove min. How many times do I do that? N times, each one takes log n time. So this whole thing is going to take n log n. However, I must stress that the one drawback of all three of these, in the way I've written it here, keep in mind you can always transform these into like the ones that you're typically used to where they're all in place. That means that you don't use any additional memory beyond a constant amount of space, and you just basically are doing manipulations on the input data. I give a definition in the notes for that if you're curious. This here, all of these, when you use this scheme, will take an additional. They'll use a big old n extra space. Do you see that? So I have to construct the priority queue. That's the big drawback of all three of these. Do you see that? So I have to build the heap. Now keep in mind, Heapify, now this is why I want to bring up Heapify, and this is why I talked about Heapify, is that there's a way to get around that big O of n extra space. Now, I must stress that this big O of n extra space only applies to this scheme and how I've discussed it here. So there's a way to implement selection sort with big O of 1 extra space. There's insertion sort with big O of 1 extra space. Those ones you learned probably in a previous course. However, I haven't showed you how you can do it with a heap. So let's talk about that. So let's talk about how you would do this. So can we avoid this? Can we avoid the extra space? The answer, of course, these ones, these are all, you've seen these before. You just have the array, you perform the operations directly on the array where you permute elements. Or you do insertions, or you find the element, then you move them around. It's just shuffling. Those ones you know how to do. This one, yes, you can also do that as well. So I'm going to describe that to you right now. So you're going to use a max heap instead of a min heap. Now I must mention that if you use a min heap over a max heap, you'll just get the elements in reverse order. So instead of smallest to largest, you'll get them from largest to smallest. So it's worth noting that if you look at the algorithms that I've given you, this can be done. So remember, max heap is just where you have the root having the largest key or one of the largest. And then what happens is all the keys below it, its children have to be either equal to it or smaller. So it's in contrast to a min heap where I look at my element, all my children either are equal to me or bigger. So this could be done by changing all less than to greater than, and all less than or equal to greater than or equal when comparing keys. In our algorithms. So all you do is you just perform this small little change. Now it's worth noting that in an object-oriented language like Java, you can use a comparator. And what you can do is you can change how the comparator operates using, because comparators operate on comparable objects. But I'm not going to talk so much about that here, but there's a simple way of tweaking around with those to make this happen without having to hard code your algorithms. So if you want that simple little change, it's not very hard to get. Either way, you can make this simple manipulation on every one of the steps where you do a comparison of the keys. You just make this small inversion. That's it. So instead, what we're going to do is we're going to start with Heapify. So remember, instead of building one entirely from scratch, we're just going to start with Heapify on the input array A. So in sorting it, remember I'm given an array A and I want to sort it. So you would apply Heapify on A. Then you would do the following. Then for I is equal to n minus 1, n minus 2, so this would be a loop, all the way down to 2, then 1. What you're going to do is you're going to do basically a remove min operation, but it's not really exactly. You'd have to make a small modification to it. Swap a sub I with a sub 0, which a sub 0 is the maximum in a max heap. Then update the heap using the modified bubble down. So you would use bubble down, but remember bubble down I had to change it slightly because of this first point. I switched the inequalities around. I'm going to use bubble down on 0, and the end index is going to be I minus 1. Why I minus 1? You're going to see. This is really neat. Note that the heap consists of indices 0 to I minus 1, and the sorted elements are in positions I to n minus 1. So as we do this process, what will happen is the left side of your heap will consist of the unsorted elements so far. Then as we shrink the heap, because remember, as we remove elements by every single time I do basically what's a remove min, what happens is my heap shrinks, but it leaves a lot of occupied space. What I do is I put the maximum in the next available spot for which I perform the swap. And you'll see that every time I'm doing this, I'm going to be filling from right to left the sorted elements. So I'm going to do an example of this. So let me do an example. And this will be the last thing we'll talk about explicitly about these. So let me let me give you an array. I think I'm going to use the same array I used the other day. Let me use 8, 2, 7, 3, 4, 1. I think this is a good opportunity for me to show you how you build a max heap. So remember I have remember these nodes technically have things in them, but I just don't want to indicate that this is in fact a max heap yet. So remember, I have this structure in play. And there's nothing here, right? Because I have 6 elements, not 7. Okay. So what I'm going to do is I'm going to build myself a max heap. So So remember, I don't have to consider all these because remember, each one of these is a subtree, which is a max heap. So now I consider this element, 7. So where's 7 located? Where's 7 located? It's right here, right? So what I do is I look at this and say, okay, well, okay, 7's right there. Do I need to bubble down anything? Now remember, this is a max heap, not a min heap. I have no right child, so I look at my left one. Is my left one less than this one, or is it equal to it? Well, this is bigger, so we're okay. We don't have to do any swapping. So by doing this, I've merged this subheap, or this partial heap, with this node to make a bigger heap. So that one's done. Okay, how about this one? Say 2's right here. Do I have to do anything? I have 2 children. Now, all I have to do is, okay, I need to maintain that this is a max heap. So I'm going to merge these two smaller heaps by putting this here. Okay, 3 or 4? I should pick 4 because it's the biggest of the 2 children, right? So remember, instead of being the smallest of the 2 children, now I take the biggest of the 2 children. So now I put 4 here. I put 4 here, and 2 goes down here. And then, what happens? Now I have to consider the last element here, 8. Okay, 8. Do I have to do anything? I'll let you think. Do I have to do anything? No, right? 8 is bigger than 4 and 7, so we're done. So I built my max heap. So this is indeed a maximum heap. Now let me just rewrite the array because I wasn't keeping track of that as I was doing things. Let me update this for you. You can check this if you like. 8, 4, 7. So 8, 4, 7. Actually, let me read it from here. I don't have to look at my notes. Silly me. 8, 4, 7, 3, 2, 1. 3, 2, 1. Yep. See, like I said, you just read it level by level. Left to right. Top to bottom, left to right. Okay? Now what we're going to do is I'm going to remove the max element and then I'm going to place in the next empty spot in the array. So what am I going to do? I'm going to remove 8. I remove 8. Remember, I give it to the weird hermit guy that's in the corner. So remember, I give 8 to that guy. So 8's over here. I put 1 here. So 1's there. But I want you to observe that when I get rid of this now there's one spot that I can put 8 into. So now 8, I'm going to stick 8 right here. Now to make this a little easier to see, I'm just going to put a bar up here. So now this is not a part of the heap anymore. That's why we need to have an end index. So now what I do is I perform bubble down on this heap, ignoring that last position, because there's no heap there anymore. So now, look, okay, I have 2 children, I switch, and thus that means that I need to swap 7 and 1. 7 and 1, so 7 and 1 get swapped. Right? 7 and 1. Okay, next. Remove the max 7. So 7 goes. 7 goes, I give it to the weird hermit guy. And then 2 goes up here. Now remember, the heap only exists here now, right? So 2's up here. Do I have a max heap? No, I don't. I take the larger of the 2 children. So 4 goes here. Do I have a max heap yet? No, I bubble down more. I need to bubble down more. So 3 goes here, 2 goes there. And then, so that means that we need to change up our array a little bit here. So this is 4, 3, 1, and then 2. Now remember, all of this over here is not a part of the heap anymore. It's just a part of the array. But notice as I'm doing this, it's always decrementing the amount of elements, and I'm occupying those spots with the assorted contents. Okay? So now we got 4, 3, 1, 1, 2. Remove 4. 4 goes here. I put in 2. 2 goes here. And remember, this is now right here. Do I have a max heap? No, right? I have to swap 3 and 2. Okay. So I just keep doing this, and you'll see very quickly that I remove 3. 3 goes here, 1 goes there. So 3 goes here, 1 goes there. Yeah, 1 went up here. And then I perform the swap because it's not a max heap. Remember, all of this up here is already part of our partially sorted array. Then what I do is I do another remove. And then I put 1 here. This goes away. We have a max heap. But look at this. I have the entire array sorted. And we're done. So I don't have to do anything with this. I just give you back this whole thing. And it's sorted. See, this, what we've just described here, these modifications, this is called Heap Sort. This is known as Heap Sort. So just keep in mind, it takes n log n time. And in terms of the auxiliary or extra space, or what we were calling space complexity in this course, it takes up, it uses constant amount of extra space, which is pretty good. So it's worth noting that in terms of time, it is comparable with things like merge sorts. So this meets actually, if you're wondering if you can do any better than n log n time, at least when it comes to this amount of space, you're not going to do any better. N log n is actually the lower bound on sorting. So heap sort is pretty good. So that concludes talking about sorting. Now I want to revisit something. I've been talking a little bit about this strange thing about arrays and doubling arrays, and I keep saying that, oh, it's a pretty good idea to do that. I want to be able to justify that for you. Okay, so I'm going to consider this an introduction to amortized analysis. So this is not by any means meant to be a comprehensive look at this topic, because this is a giant rabbit hole. But I want to show you this because in data structures, this approach, this type of analysis is quite prominent, especially these days, because it's quite useful in its own regard. So I'll motivate it first, and then I'll give you some definitions. So very often, we have considered scenarios where we have an array that may be resized. So a so-called dynamically sized array or a resizable array. We've talked about actually some examples of this in this course already. So can you think of some examples? So one example I can think of is that when we have like put operations in an array-based dictionary. So for example, if we run out of space in an array, we'd have to allocate more space. So we have to copy all the, so I start off with an array, and then I perform I allocate more space, so usually twice as much. I'll explain why. Sometimes people will say twice as much. And then I do is I copy each one of those elements, and then I perform the insertion. So I would insert normally, but if I run out of space, I create another array, I copy all the elements into it, and then I insert the element that couldn't fit. Okay? So that's something I would do. So how about hash tables? That was another example where we had to rehash the table, and I told you some good ideas for when to rehash. What's another one? Well, the main reason why I'm bringing this up right now is the array-based heaps. Because I showed you a nice and simple way of implementing a heap using an array. And I said some stuff earlier when I was talking about the running times, when I talked about these arrays, and I made an assumption that's underlined where I said, okay, well, we're going to assume that the array, we already know what the size of the array is. So the big thing I want to point out and why I made that assumption involving heaps was because normally we assume that this bad situation where we have to resize the array doesn't happen, but it can happen. So I'm going to say oftentimes, classic worst case analysis may not capture a more realistic scenario where faster insertions or deletions occur very often and expensive operations not so much. So this happens all the time, right? In data structures, especially if arrays are involved, where we have it where, okay, well, we normally would have to account for this. Oh, well, there might be a possibility we have to resize the array, so we have to include that in the worst case running time. It ends up being too pessimistic in terms of the analysis. So what we're going to do is we're going to take a bit more of a careful approach. Let me illustrate this by an example. So just so I can write something down with you, which will illustrate the scenario we're going to be talking about when we talk about amortized analysis here. And you'll find very quickly that it's very easy to extend the idea I'm going to talk about here to a lot of the things we've talked about, which is why I'm not going to talk much about amortized analysis in other parts of this course. Okay. So here's an example. Put operation. So we're going to consider a put operation on an unsorted array. So there's two possibilities on a put, right? So when an array is not full, it takes constant time, right? So you do this in the cutest way possible. You just keep track of how many elements you have so far. You insert it into the spot that you can freely put it in when it's not full. However, when the array is full, it takes linear time. aggregate time. So remember, I have to create a longer array, I have to perform some copies, and then I do an insertion. So here I just do the insertion directly. So an insertion. And then here I have to do copies. So I have to copies. So I have to perform copies and an insertion. So I do copies and an insertion. So what's amortized analysis? So amortized analysis. The analysis of a sequence of operations as opposed to a single operation. Remember, we established doing single operation analysis like that can be sometimes way too pessimistic. We will consider the worst case running time per operation. So it isn't just the worst case running time, it's the worst case running time per operation. That's what makes this amortized. I must stress that this is not average case analysis. Remember, average case analysis is over a distribution of instances where you compute the running time in the expectation, right? So just to wind things up, I'm just going to define what is called the aggregate method, which is one of the standard techniques, and it falls right out of this concept. So we have a sequence of operations, and what we're going to do is we're going to, now remember, these are typically things you would define. You define the sequence of operations, and then in amortized analysis, you look at the worst case running time per operation. So there's a nice natural way of looking at this. It's called the aggregate method. This is the one I'm going to talk about in this course. It's called the aggregate method. So this is how you do the analysis here. And it falls right out of this definition. If the total cost or time, you can think of it as time or cost, of performing n operations is big O of Heapan, then the amortized cost or complexity of the operation is, what is it? It's big O of T of n divided by n. That's what the aggregate method is. And it falls right out of the definition of what we've given here. So amortized analysis is a kind of worst case analysis where we're going to consider the worst case running time per operation. So I'm going to count up all the total time it takes for my operations over that sequence. I'm going to divide it by the number of operations. Okay? So next day we'll see some examples of doing this. I'll show a lighter way and then I'll show you a deeper way. Okay? So thank you very much. Have yourself a beautiful day.